Right now, you're being pulled toward the center of the Earth, 9.8 meters per second squared. You don't feel it because the floor is pushing back. That's it. That's the whole trick. But pull that floor away, and gravity wins. Every time. No exceptions. What nobody really explains, what the textbooks skim over, is that this pull doesn't stop at the floor, doesn't stop at the atmosphere, doesn't fade out somewhere past Pluto. It keeps going. Light years, galaxy clusters, 93 billion light years of observable space. Gravity doesn't fade, it spreads. And in some places out there, it gets so extreme that even light can't escape it. This is the full story of the force that built everything and still won't let go. Think about the last time you dropped something. Your keys, your phone, face down, obviously. Here's the thing nobody tells you about that half second of free fall. The object didn't fall toward the Earth. Not exactly. The Earth and that object fell toward each other. We just never noticed the Earth side of it, because Earth outweighs your phone by about 6 septillion to 1. Its movement is too small to detect, ever. Isaac Newton figured out the math in 1687. The Apple story is almost definitely embellished, but what he actually worked out was real. Every object with mass pulls on every other object with mass. The strength of that pull comes down to two things: how massive each object is and how far apart they are. Double the mass, double the pull, double the distance, drop it to a quarter. That's the inverse square law. It's why the Sun holds Jupiter in orbit from 778 million kilometers out. Why the Moon raises ocean tides on opposite sides of Earth at the same time. Why you'd weigh about 17% of your normal weight standing on the Moon, and why you'd be crushed flat on the surface of a neutron star. Same force, wildly different outcomes depending on what you're standing next to. But Newton's equations had a problem, a real one that nagged at physicists for over 2 centuries. His math said gravity was instantaneous. Move a massive object anywhere, and every other object in the universe supposedly knows about it right away. No signal sent, no delay, no actual mechanism. Just instant knowledge across any distance at all. Physics doesn't work that way. Nothing in physics works that way. In 1915, Einstein published the general theory of relativity, and it didn't add to Newton's work. It buried it. Newton thought gravity was a force, an invisible hand reaching across empty space, pulling things together. Einstein said no, gravity isn't a force at all. It's what happens when mass warps the fabric of space and time itself. Space and time, in Einstein's picture, aren't a passive backdrop where physics happens. They're a physical structure, a geometry, and mass bends that geometry the way a bowling ball bends a rubber sheet. Picture it, a flat, even grid, stretched taut. Drop something heavy into the center. The grid curves around it. Now roll a marble across that curved surface. It doesn't get grabbed by anything. It just follows the shape of the surface it's traveling through. Mass tells space-time how to curve. Curved space-time tells matter where to go. That's gravity. That's what it actually is. When you step off a ledge and fall, no force is grabbing you. In curved space-time, the path that takes the least energy, the path of free motion, runs downward. Following that path isn't being pulled, it's just moving freely through bent geometry. Think about what that means for right now. Floating in deep space, no rockets, no massive objects nearby. That's what zero acceleration feels like. Nothing acting on you. True free motion, but sitting wherever you are right now, you're being accelerated upward at 9.8 meters per second squared. The floor is pushing you continuously against the curved geometry of space-time beneath the planet's surface. Gravity isn't pulling you down, the ground is pushing you up against it. And that reframing has a consequence that nobody in 1915 was quite ready for. If gravity is a distortion in a physical structure, that distortion can only travel through that structure at one speed, the same speed everything propagates through space-time, the speed of light. Move a massive object, and the change in curvature ripples outward at 299,792 kilometers per second. Not instantly. If the sun vanished right now, physically impossible, but follow it, we wouldn't feel the gravitational change for 8 minutes and 20 seconds. Same delay we'd wait before the sky went dark. Einstein predicted this in 1915. A century passed before we could prove it. We'll get there. Let's go back to the inverse square law for a second. Double the distance, gravity drops to a quarter. Triple it, drops to a ninth. 10 times the distance, 1/100th. But here's what the equation never does. It never hits zero. Multiply the distance by 1,000,000, 1,000,000,000,000. The number of atoms in the observable universe. Gravity keeps going. It approaches zero, yes, closer and closer, forever, but it never actually gets there. There's no distance at which it simply stops. Your body right now has a gravitational pull that technically extends to the edge of the observable universe. Unmeasurably small, below anything we have instruments for, but not zero. And this isn't a thought experiment. It has real, visible consequences. The Andromeda Galaxy is 2.537 million light years from us. It's also heading straight for us. That's gravity, acting across 2.5 million light years of empty space, pulling two entire galaxies toward each other, silently, for billions of years. In about 4.5 billion years, they'll meet, not in an explosion, not in a single flash. They'll pass through each other slowly, over hundreds of millions of years. The stars too spread out to physically collide, but their gravity reshaping everything, pulling individual stars into completely new orbits, until two spiral galaxies gradually become one elliptical mess. Patient doesn't even begin to cover it. And it's not just these two. The Coma Cluster, thousands of galaxies spanning 20 million light years, all held in mutual orbit. The Virgo Cluster, the Perseus Cluster, a Bell 2029, structures at a scale that barely fits inside the word structure, all organized by gravity pulling across distances that make our entire solar system look like a rounding error. All the visible matter in those structures, though, turns out to not be enough to explain it. Something else is doing some of the holding, something we can't see. In the 1970s, astronomer Vera Rubin was mapping how galaxies rotate, and the numbers she was getting made no sense. Stars at the outer edges of spiral galaxies were moving too fast, way too fast, based on everything visible, every star, gas cloud, dust grain. Those outer stars should orbit more slowly than the ones near the center. Same principle as our own solar system. Neptune crawls at 5 kilometers per second. Mercury races at 48. The farther from the source of gravity, the slower the orbit. Except galaxy edges weren't doing that. Rubin found that rotation curves were nearly flat. Outer stars moving at almost the same speed as inner ones. Not one galaxy, not two. Galaxy after galaxy after galaxy. It wasn't instrument error. It was completely consistent. The only explanation that fit: there's a massive amount of matter in those galaxies that we simply can't see. Something forming an invisible halo around each one, providing gravitational pull without emitting any detectable light, heat, or radiation. We call it dark matter. And it's not a small correction. Dark matter makes up roughly 27% of the universe's total mass energy content. Everything you can actually see, every star, every planet, every galaxy, this planet, that totals about 5%. We are apparently living inside the 5% that showed up. Dark matter doesn't interact with light at all, doesn't emit it, doesn't absorb it, which is exactly why we can't see it, but it still has gravity, and gravity bends light. When a massive concentration of dark matter sits between Earth and a distant galaxy, its gravity curves the light from that galaxy around it, like a lens. We see distorted arcs, stretched images, sometimes multiple copies of the same galaxy, bent into perfect geometric shapes by something that isn't there, visually speaking. Hubble's image of galaxy cluster Abell 2218 is one of the clearest examples we have. Perfect arcs of lensed light, entire background galaxies stretched and curved around the foreground cluster by gravity, much of it coming from dark matter that isn't directly visible in the image at all. We've mapped its distribution across most of the observable universe, using only the shadows it casts on light from things we can see, and we still have no idea what it actually is. Every plausible candidate particle has been hunted. Weakly interacting massive particles, axions, sterile neutrinos, detectors buried kilometers underground, waiting for a single collision event. No confirmed detection yet. We can weigh it, map it, trace its edges with real precision, and we don't know what we're weighing. That's where we are. To understand what gravity looks like at its absolute limit, you have to look at what happens when there's nothing left to stop it. A stellar black hole starts as a massive star, at least 20 times the mass of our Sun. The whole time that star is alive, fusion reactions in its core push outward, constantly fighting gravity. Heat against collapse, a balance that holds for millions of years. Then the fuel runs out. The support disappears in under a second. The core collapses. The outer layers explode outward in a supernova, and the inner core keeps falling past the density of a neutron star, past any physical structure we know of, down to a single point of theoretically infinite density, a singularity. Around it, space-time curves so severely that there's a point of no return, the event horizon. Inside it, the escape velocity is higher than the speed of light. No particle gets out, no signal, no information of any kind, nothing. But here's where black holes get genuinely strange, philosophically strange, not just physics strange. The event horizon isn't a wall. There's nothing there to hit. If you fell toward a supermassive black hole, you'd pass right through the horizon without feeling anything unusual, at least from your own perspective. You might not even notice, not right away. From outside though, someone watching you fall would see something completely different. Time near extreme gravity runs slower relative to everything else. The closer you get to the horizon, the more your clock falls behind. The light trying to climb back out of the gravitational well loses energy as it climbs. It redshifts, stretches to longer and longer wavelengths. To an outside observer, you'd appear to slow, then nearly stop, then fade, redder and dimmer, asymptotically approaching the horizon. You'd appear to never quite cross it. In April 2019, the Event Horizon Telescope released the first actual image of a black hole. A global network of synchronized radio telescopes, effectively a single Earth-sized dish, captured M87 star, the supermassive black hole at the center of galaxy M87. 6.5 billion solar masses, an event horizon larger than our entire solar system. The image, a bright ring of superheated plasma orbiting the black hole, and a dark circle in the center where the light simply doesn't come back. It matched Einstein's equations exactly. In May 2022, the same team released an image of Sagittarius A star, the supermassive black hole 26,000 light-years from us, at the center of our own Milky Way. 4 million solar masses, the same ring, the same dark center, the same conformation. Black holes aren't exotic edge cases. They're physics taken to its natural conclusion. They're what you get when gravity has no competition left. September 14th, 2015, 5:51 in the morning, Eastern Time. 2 detectors in the United States recorded something. The LIGO observatories, one in Hanford, Washington, one in Livingston, Louisiana, are built around an idea so precise it's almost hard to believe anyone tried it. Each is an L-shaped vacuum tube, 4 kilometers per arm. A laser beam splits, runs down each arm, bounces off a mirror, and recombines at the center. When both arms are exactly the same length, the beams cancel perfectly. When a gravitational wave passes through and stretches space-time in one direction while compressing it in the other, the arms become fractionally different lengths. By fractionally, I mean 1,000 times smaller than the diameter of a proton. That Tuesday morning, the signal lasted less than a second. A rising chirp, GW150914. Two black holes, each about 30 times the mass of our sun, had been spiraling toward each other for billions of years. In the final 0.2 of a second, they were orbiting each other 75 times per second. The merger produced one black hole of 62 solar masses. 3 solar masses of matter had been converted entirely into gravitational waves, released in a fraction of a second. In that fraction of a second, the power output exceeded every star in the observable universe combined. Every single one of them. Einstein predicted gravitational waves existed in 1916. 100 years later, we built something sensitive enough to feel one, and on a quiet Tuesday morning in September, Spacetime rang. 2 years after that, 2 neutron stars merged 130 million light-years away. The gravitational wave signal arrived at LIGO first. Then, 1.7 seconds later, satellites and ground telescopes around the world detected a gamma-ray burst from the exact same event. For the first time, we'd caught one cosmic event through 2 completely different windows, gravity and light, both arriving at Earth from the same source. We'd been watching the universe for all of human history. That day, we started hearing it.
We heard it.
Gravity isn't even. It's not the same at every point in space. And that difference, that gradient, has consequences that are difficult to describe without sounding like science fiction. When the near side of an object feels more gravitational pull than the far side, the object stretches toward the source and compresses inward from the sides. The moon does this to Earth right now. The ocean facing the moon gets pulled slightly harder than Earth's center. Earth's center gets pulled slightly harder than the ocean on the far side. 2 bulges, 2 high tides, every rotation. Near a stellar black hole, this process stops being subtle. Fall toward the singularity feet first, and the gravity at your feet is measurably, catastrophically stronger than at your head. That difference alone exceeds what any physical structure can withstand. You'd stretch lengthwise and compress inward simultaneously. Spaghettification, that's the actual term, not a metaphor. It's what the tidal force equation predicts. It's what would happen. In 2019, we watched it happen to a star. 375 million light-years away, a star drifted too close to a supermassive black hole. The tidal differential tore it apart, half the stellar material flung outward in a debris stream, the other half spiraling inward, forming a glowing disk that blazed in X-ray and optical light for months. The event was designated AT2019 KIS, the closest and most detailed tidal disruption event ever recorded. The match between observation and theory was precise enough to reconstruct the entire timeline of the disruption, beginning to end. Gravity doing exactly what the equation said it would, to a star. Here's something that should feel genuinely strange when you sit with it. Gravity is the weakest of the four fundamental forces, and not by a little. A refrigerator magnet, that small thing holds itself against Earth's gravity. The electromagnetic force of a piece of magnetized iron the size of your thumb defeats the gravitational pull of a 6 septillion kilogram planet. Electromagnetism is roughly 10 to the 36 times stronger than gravity. The strong nuclear force, which holds protons and neutrons together inside atomic nuclei, is about 10 to the 38. Gravity isn't just the weakest force. It's weaker than everything else by a margin that doesn't fit on a normal number line. So why does it run the universe? Because there's no off switch, no negative version, no anti-gravity canceling it out. Electric charges come in positive and negative. At large scales, matter is mostly neutral. The fields cancel. Nuclear forces only exist within the width of an atomic nucleus and don't reach outside it. Gravity has no counterpart. It only accumulates. Every bit of mass adds to the pull, without ceiling, without cancellation. At small enough scales, it's irrelevant. Electromagnetism runs chemistry, nuclear forces run atoms. But at large enough scales, galactic scales, cosmic scales, all that accumulated weakness adds up to something that overwhelms everything else in the universe. The weakest force, running the largest structures that exist. In 1998, two independent teams of astronomers were studying distant Type 1a supernovae, standard candles for measuring cosmic distances. Neither team was looking for anything strange. Both teams found the same thing. The universe isn't just expanding after the Big Bang, it's expanding faster and faster. Something is accelerating that expansion, pushing space itself apart at an increasing rate. We call it dark energy, and it makes up about 68% of the universe's total mass energy content, more than all matter, visible and dark combined, by a wide margin. For most of cosmic history, gravity was the organizer. It pulled gas into stars, built galaxies, grew clusters, wove the vast web of filaments and voids that gives the universe its large-scale structure. For billions of years, gravity was winning, but dark energy was always there, quiet, diffused, embedded in space itself. As the universe expanded and the total volume of space grew, dark energy's influence grew with it. About 5 billion years ago, the scales tipped permanently. Dark energy won. Gravitationally bound structures, galaxy clusters, galaxies, solar systems are still held together. Locally, gravity still runs things, but the space between unbound regions is growing. Galaxies with no gravitational connection to us are already receding faster than light, not because they're moving through space at superluminal speeds, but because the volume of space between us is inflating. Gravity spent 13.8 billion years building the structure of the universe. Dark energy is now taking it apart, one expanding void at a time. So, Why does gravity never let go? Mathematically, the inverse square law has no zero. The reach of space-time curvature has no boundary. As long as mass exists, there is curvature. As long as there is curvature, there is gravity. But under that, there's something more fundamental. Gravity isn't a force that lives in space. It is the shape of space. And you can't escape the shape of space by moving through it, because you carry mass, and mass warps the geometry around you wherever you go. There is no outside of space-time to retreat to. There never was. Every atom in your body was forged in the core of a star that died before our sun was born. Gravity compressed that star's gas cloud until it ignited. Gravity drove the fusion that built the carbon, the oxygen, the iron, the specific atoms you're assembled from right now. When that star died, gravity shaped the explosion that scattered those atoms across light years of empty space. Then gravity pulled them back, slowly, into the nebula that became our sun and this planet. Gravity held the early oceans in place, held the atmosphere down long enough for chemistry to turn into biology. You exist because of a chain of gravitational events that started billions of years before the Earth did. And in billions of years, when the atoms you're currently made of have been scattered and recycled and scattered again across some future galaxy, gravity will still be acting on them. It won't have forgotten. Gravity isn't a number you memorize for a test and forget. It's the reason everything that exists is where it is. The universe didn't build itself from the bottom up. It fell together from all directions at once over billions of years because gravity gave falling a direction. Next time you set something down and watch it stay there or catch yourself mid-fall, that's general relativity, that's space-time curvature, that's geometry telling matter exactly where to go. If that changes how you think about the ground beneath you, we make these every week. And if you want to see what happens when two supermassive black holes finally find each other, that video is right above this one. See you out there.